here we're going to go over 2021 AP Calc AB FRQ number 3. This seems to be the problem that got the most fanfare amongst students. And so let's read it, and then we'll go ahead and jump into letter A. So it says a company designs spinning toys using the family of functions y equals c times x times the square root of 4 minus x squared, where c is a positive constant. Figure above shows the region in the first quadrant bounded by the x-axis and the graph of that function for some value c. It says each spinning toy is in the shape of the solid generated when such a region is revolved about the x-axis. Both x and y are measured in inches. And I really think that one of the reasons why this question was so confusing for students is because of the fact that they tied in normal solid revolution problem into talking about spinning toys. I think if they had just left it as a function and not put some scenario with spinning toys in there, probably students wouldn't have been as intimidated by it. But we'll talk about how all that relates as we go in right here. So it says, first of all, find the area of the region in the first quadrant bounded by the x-axis and the graph of y equals c times x times the square root of 4 minus x squared for c equals 6. So essentially what they're saying is for this problem, we have this function, and we want to find the area that's bounded by the x-axis in this graph. Okay, so that would be essentially this area right here. Well, before we do that, we need to figure out what the x-intercepts are for this function. So I'm going to begin by setting this function equal to 0 and trying to solve for x. I know that I'm going to get 6x equals 0 and this is equal to 0. We're only trying to find values in the first quadrant, so we only need positive x values here. So I'm going to get x equals 0. We can see that from the graph. On this next one, I'll get 4 minus x squared equals 0. You can either do the math for that or just recognize that the only positive x value that will make this true is when x is equal to 2. So essentially, all we're attempting to calculate on this problem is the area under the curve from 0 to 2 of this function right here. Okay, so this is just a u substitution problem, and we're going to evaluate this integral and see what we get when we're done. So I'm going to go ahead and start out by setting u equal to 4 minus x squared, which means du is negative 2x dx. Well, currently we see a 6x under there, so I'm going to go ahead and multiply both sides by negative 3. So when I'm done, I get negative 3 du equals 6x dx. Okay, so now I can start working with this integral a little bit. I'm going to take that negative 3 and move it out to the front. Okay, so now I'm going from 0 to 2 of, and now I can rewrite what I see underneath the integral here. So I have the square root of u, because 4 minus x squared is u, du. Okay, all right, good way of thinking about the square root of u is to think about it as u to the 1/2. And that makes the problem a little bit easier to do. One thing that I noticed as I'm writing this down, I would actually get this problem completely wrong if I left these bounds of integration as they are right now, because I changed this problem to being in terms of u, so I need to change my bounds of integration to being in terms of u as well. So I'm going to go ahead and plug those in here. If I plug in 0 over here, 4 minus 0 is 4. Okay, and when I plug in 2, 4 minus 4 is 0. Okay, so maybe some students will just go ahead and evaluate it like this. Most of the time I teach my students, if the bounds are flipped, go ahead and pull out a negative and flip those bounds back. So now I'm going to rewrite this in this way, and now I'm going to try it. So now I'll find the antiderivative of u to the 1/2. Add 1 to that power, I'll get u to the 3/2. And divide by 3/2, so this will be a 2/3 out front. There's already a 3 out here, and I would like to evaluate this using the fundamental theorem of calculus at 4 and at 0 and subtract those values. I'm going to go ahead and cancel out these 3's right here. Okay, and so when I'm done, what I really get is 2 times 4 to the 3/2 minus 0 to the 3/2. And you could leave it like this if you'd like, but you can go ahead and go a little bit further here. 4 to the 1/2 is 2, and then 2 cubed is 8. So this becomes 2 times 8. So the final answer to letter A here is 16. Okay. All right, going over to letter B. Let's look. It says it is known that for our function, and they give us the derivative. They don't even make us calculate this ourselves, which says for a particular spinning toy, the radius of the largest cross-sectional circular slice is 1.2 inches. What is the value of C for this spinning toy? All right, so First thing that you have to do on this problem is we need to make the connection that in the location for the largest cross-sectional circular slice, let me just draw so I don't have to scroll back and forth here real quick. So here's our shape, okay, something like that. And so the first thing you have to recognize is that the largest cross-sectional circular slice is going to occur at, in this case, at our relative max, okay? Because the largest radius occurs right here. All the other radii, as you move up and down that region, are smaller. And so we need to make the note that when, or that y equals, sorry, I should say, when y equals 1.2, because that's going to be the height or the radius, dy dx is equal to 0, okay? Because the derivative of a tangent line is equal to 0. So what I'm going to start out by doing here is I'm going to say, well, let's see if we can figure out what the x value is when the derivative is equal to 0, because they gave us the derivative itself here, dy dx. So I'd like to see if I can set that equal to 0 and solve for x, and then I can use that to help me solve for c, because that's what we're actually trying to figure out. So I'm going to go ahead and start out by setting this up. Okay. And so as I'm kind of walking my way through this here, what I know is that in order for this to be true, the top of this has to be equal to 0, okay? So when I'm done here, I would have 0 equals c times 4 minus 2x squared. Well, c is some constant, so I know c can't be 0, but I do know that the x value that would make this 0 would occur if this were true, okay? So I'm going to go ahead and solve this real quick. So let's see, a lot of algebra here on this problem. X squared equals 2. And so when I'm done here, I get x equals technically the plus or minus square root of 2. Since we're working in the first quadrant here, I know that this occurs when x is equal to 2. Okay. Now we haven't solved for c yet, but what I can now do is I can say, well, here's the function y equals c times x times the square root of 4 minus x squared. And I now know what y is, and I also now know what x is, so I can plug those in, and I can use those to help me solve for c. So that's what I'm going to do. Well, y I already know. The largest radius for the cross-section was 1.2 times is equal to c times the square root of 2 times the square root of 4 minus the square root of 2 squared. Okay, let's do a little bit of math and evaluation here. This is the square root of 2. 4 minus the square root of 2 squared. Well, the square root of 2 squared is 2. 4 minus 2 is also the square root of 2. Okay, so square root of 2 times the square root of 2 is 2. So when I'm done here, 1.2 divided by 2, I get that c is equal to 0.6. Okay, fairly confusing question right there with a lot of different connecting parts. But if we understand this idea of the derivative having to be 0 wherever that largest cross-sectional radius is at, then we can kind of work our way through the problem from there. Okay, all right, let's go over to letter C. It says, for another spinning toy, the volume is 2 pi cubic inches. What's the value of C for this spinning toy? Well, this is a volume of revolution problem, although they're actually making you solve something with it. So if we think about the volume of revolution real quick, just write down this formula. Volume of revolution is equal to pi times the integral from a to b of a larger radius squared minus a smaller radius squared dx. Although in this case, because of the way that this shape works, there's no inner radius. So for us, this would just be 0. And the outer radius would be whatever our function is, which they gave us in the problem, obviously. So I'm going to go ahead and plug that in, and then we can start thinking about what this would look like. So for us, it's going to be pi times the integral from, we already know, from 0 to 2 of c times x times the square root of 4 minus x squared dx. Okay, so that's our integral for how we would figure out the volume of any of these shapes if we were to actually rotate them around the x-axis right here. Okay, now they tell us that the volume is equal to 2 pi. So our goal is now, actually I'm just going to go ahead and erase this b here and do this. Our goal is now to take this equation, and this is why this is a very algebraic problem, all parts of this free response. And we're going to solve for C, okay? So I'm going to start out by dividing both sides by pi, just to get that out of the way. So when I'm done here, I get 2 equals, and you go from 0 to 2. I'm going to go ahead and apply that squared. So I get c squared times x squared times square root squared cancels out, and I'm left with 4 minus x squared dx. Okay, and from here we're just working our way through an integral. Okay, I can take this c squared. This is a constant, so if I'd like, I can pull this out to the front. Okay, and I'm going to go ahead and distribute this x squared right here. So I'm going to have 4x squared minus x to the 4th dx, and now from here I can start taking the antiderivative. Okay, so antiderivative, I'll switch colors for this. I'm going to have x cubed. Okay, 4/3 x cubed, and this one will be minus 1/5 x to the 5th, and we'll evaluate those from 0 to 2. Okay, so 2 equals c squared times. All right, let's see. If I plug in 2 right there, 2 cubed is 8 times 4 is 32, so this will be 32 thirds minus 2 to the 5th is 32, so minus 32 fifths. And I'm going to go ahead and write this, but when I plug in 0 to both of those, I'll just get minus 0. Okay, and there's really no reason for us to evaluate this, especially on a non-calculator problem. So when we're done here, I'm going to write this as 2 divided by 32 thirds minus 32 fifths. Okay, and then to solve for c, I'm going to take the square root of both sides. And when I'm done, here's what I end up with, okay? And again, technically this should have a plus or minus out in front of it. However, since our function exists in the first quadrant, we're looking for a positive c value. So when I'm finished, here's my final answer. And that concludes question 3 from the 2021 AP Calc AB FRQ.